Okay, so today I'm going to talk about the bidirectional reflection distribution function. And I shouldn't have quit early last time because there were a couple of other topics that I should have talked about last time that I'll try and squeeze at the end of this time. So the idea is when you have reflection, a certain amount of the light that's coming in comes out in a reflected direction. And in general, that can depend on both the incident direction and the reflected direction. So that's why it's called, I should actually write the words down, bidirectional. So to continue the end of that sentence, that's why it's called bidirectional reflection distribution function. So the reason it's called a distribution function is if light comes in and hits a surface, unless that surface is a perfect mirror, the light will come off in all directions, or a lot of directions anyway, and the amount of light that comes exactly in any specific direction, say capital phi, theta, is zero. It's just a quantity that you have to integrate to get the light that comes in a finite region of directions on the unit sphere. How can I think about that? You know, if a finite amount came in every direction and there are an infinite amount of directions in the unit sphere, then the total light reflected would be infinite. It's a quantity that you have to integrate to get a number, and that's why it's called a distribution function. So basically, we're going to have a radiance that comes out. A radiance is already amount of light per solid angle. So the radiance can be finite amount because it's already got the implicit solid angle involved in it. But in terms of a distribution function, the actual amount of light that comes out in any given exact direction is zero. That's why that part of the name. So what we'll talk about is, let me think, how can I do that correctly then? I can still talk about a radiance coming out. And I can talk about a radiance reflected. And the notation in the book is they call this the radiance reflected at position x going out from x in direction theta. And the reason they put a D on it is because it's the radiance reflected in that direction for radiance coming in, not in an exact direction, but in some solid angle around that direction. So here is the direction capital psi. It's really hard for me to write these capital letters, but I'm trying to follow the notation in the book. And what I want is a function which will, it's a constant multiple. Well, it's not a constant because it can depend on the position and it can depend on the two angles, which the book denotes by writing angle psi reflecting into angle theta with an arrow. And what that multiplies is the amount of irradiance that comes in from an angle psi. What we really are doing is a little solid angle around that. So it's this FR times the radiance flowing toward direction x from this direction psi from here, but in some solid angle, right? Because in order to get an actual amount of energy from a radiance, you also have to multiply that by a solid angle, because radiance is flux per solid angle. So to get flux per unit area normal to the beam here, we have to multiply it by this solid angle, the omega psi, and then we also have to multiply it to account for the foreshortening that we talked about last time, multiply it by the cosine of the angle, right? Because the less flux per unit area to give you an irradiance if it's slanted with respect to the thing. So I'm just going to call it cosine theta, where in the book they write it as cosine of the angle between the surface normal here. Let's see, this is perpendicular to the surface normal, and the light direction is perpendicular to this plane that I drew. And so this theta is the angle between this and the incoming light direction. And you can really just compute it as the dot product of n times that unit vector. But in general, we're only going to look at light coming in from the hemisphere above the surface. So this is always going to be a non-negative dot product. But if you want to do shading, it's better to just take the maximum of that dot product and 0. And then you know if the light is coming from below the surface, it's not going to contribute to the reflection. So what this says is this reflection coefficient depends on these two directions, and it's what you multiply the irradiance coming from some small piece of angle in this direction to get the radiance coming out. And we say irradiance because it has that cosine factor already as part of the definition of irradiance. And that means the bidirectional reflection coefficient itself is the, say, dl out. I'm sorry, that should have been an L. I was thinking of my denominator while I started writing before I finished this one. dE, say, coming in. So that's the reason for the D, because it's for a differential amount of radiance coming in near a specific direction. So that's why the definition was a dl instead of an L coming out. And that means if we want to know the total L coming out at x going out into direction theta, we have to actually integrate this over this hemisphere, say above the surface point x. We'll make this unit hemisphere, omega x, and we'll integrate the light coming in from all directions and its corresponding d with respect to this integration d omega solid angle. So that means we have to have this FR, F sub r, for light at position x coming from direction c and reflecting in direction theta, times the L coming in from direction c at x. I probably should put an x there too if I'm copying the formula out of the book. And then I have the cosine theta to turn it into an irradiance. And then I'm integrating over this solid angle of the hemisphere of incoming directions psi. So I've got, say, environmental illumination. Maybe you created an environment map by taking a bunch of photographs all from the same point and combining them. Or other people do environment maps by just putting a very shiny metal sphere and taking a picture of that, and it actually reflects light coming in from all directions toward the camera. If you knew the environment illumination, then you could compute, and you knew this bidirectional reflection function, you could compute how much light comes out in any direction. So we have to do this integral. And a lot of the course is how to do this efficiently with sampling. So let me just write one property that we'll talk about that you can prove by conservation of energy. Helmholtz reciprocity, which says if you look at this function at a position x for light coming from direction psi and reflecting into direction theta. That's the same as if you made the light come from direction theta and reflect into direction psi. So if we go back to our surface, there's a certain BRDF that says how much of this light is going this way. It's the same BRDF as if you sent the light in this way and asked how much went out that way. It sort of just says you can reverse the directions of photons, and they'll exactly track the same way in the other direction. So I want to talk about a bunch of special cases. And the first is diffuse reflection. And what that means, I said last time, is equal radiance reflected. So this is L from X going to theta in all directions theta. So the surface looks equally bright in all directions. And what we computed last time by integrating over the hemisphere was the total light that comes out was pi times this constant radiance coming out. Right? By assuming the radiance is constant and then integrating the total flux per unit area that came out and doing the variables theta and psi for spherical coordinates and doing some trig integrals, we ended up with just pi. Okay, so what that means is that L out is just B out over pi. So now I'm going to let rho equals the fraction of the incident irradiance reflected into the radiosity. So the idea is this radiosity B, maybe I should call it out, represents flux per unit area. And the irradiance coming in also represents flux per unit area. And you could call it the hemispherical reflectivity says if you integrate all the light that comes out, what fraction of the light that comes in does that represent? The rest is absorbed by the surface. And since it's a fraction, by conservation of energy, rho is less than or equal to 1. It can't be more than 1. Well, then we can get L out. You know, I'm writing subscripts in and out just because I get tired of writing all these arrows here. L out is B out over pi, which is just rho over pi times E in, or we can write it as rho over pi times the flux coming in and the solid angle. Right, so now this is a flux per unit area normal to the beam, and then we can write it times cosine theta. Because that's how you convert this to flux per unit area on the surface, which isn't normal to the beam. Right, that's just the definition of E in. And so if we think about this as some sort of illumination intensity, then this looks very much like the diffuse reflectivity formula that we have in Lambert's law. That should have been a lowercase theta, right? The angle, but of the infinite direction with respect to the surface normal. right? Biggest when it's agreeing with the normal, and less as you have more foreshortening there. Spread the light out over a larger surface. So this, I shouldn't have said equals. This is the brightness that you're going to use for shading, is just this diffuse reflectivity, which is, you know, this is our FR. Right? I should have so this rho is either, you could think of it as diffuse reflectivity, or you think of it as this coefficient FR that you have to multiply the irradiance in by to get the radiance out. So this bidirectional reflection coefficient doesn't depend on the directions if it's a perfectly diffuse surface. It's just this reflectivity divided by pi. So what that means is KD should never be 1. At most, it should be 1 over pi if you're going to be conserving energy. But some, people really, when they do computer graphics, they just try and make the picture look nice. They sort of invent the illumination that makes the picture look the way they want it. And so I guess they just make their lights dimmer in order to get... Well, actually, people just create numbers. They don't think of physical units. They just want a displayable range that, when converted to a float, from a float, say, to an integer doesn't exceed 1, which is... I'm sorry. They want a pixel color for red, green, and blue that doesn't exceed 1. Because beyond that, it wouldn't be displayable. So they don't really worry about physical units. But if you are worrying about physical units, then this KD should never be really 1. It should be, some number less than 1 over pi. Okay, so now I'll talk about perfect specular reflection. And so here we have this surface, and light is coming in this direction from some point C. And here is our surface normal. And the idea is that the perfect reflection direction was in the same plane as C and N, and made this angle equal to that angle. And in the first lecture, I drew you some sort of a parallelogram here and computed that the perfect mirror reflection direction was the incoming direction dot the normal multiplied by the normal. This is a scalar, which gives the length of this projection. If you double it, that's the length of this point, and if you subtract the incoming direction, you get the point of this vector here. So minus the incoming direction. So that's the perfect mirror reflection. But at the beginning of the period, I said if it's a distribution function, no exact direction gets all the input light. Well, that's not true in this case. If it's a perfect mirror, all the input light that comes in this direction is going to go exactly out in that direction. So this bidirectional reflection distribution function is really like a delta function. No matter what solid angle you integrate it over, you'll get the same answer, as long as that solid angle contains the direction r. And that's actually the definition of a delta function. It says, it operates by integration, and it integrates to 1 if it's a delta function in that direction over, because basically you multiply it by the constant function 1 and do the integral, you get the value of that function, if you remember the definition of a delta function. So in this case, it's not really a ordinary distribution function, because its value has sort of got to be infinite in that direction if you can integrate it over an arbitrarily small solid angle and get the same answer. But in any case, there it is, and there's actually, even for perfectly shiny surfaces, there's a specular reflection coefficient, which is the fraction of the flux that's actually reflected, because the mirror may be perfect in terms of its shininess, in terms of creating that delta function, but the mirror may still reflect, like if it was gold, it'll reflect more colors near red, yellow, and green than it will reflect blue. So this Ks actually can depend on the wavelength. And in general, if it's, say, something like a surface of glass or water, it's going to depend on the incident angle, actually for metals too. And so it depends, maybe I'll say it depends on the wavelength and this angle. And then there's no point saying it depends on the reflected direction too, because the reflected direction is uniquely computed from the incident direction. And you can derive this from electromagnetic theory, but there's a guy, Fresnel, who actually, it's a bunch of trig functions. I'll write it when I talk about refraction, because the easiest way to compute it actually is in terms of thinking about the refraction direction. And he derived it empirically. It's got a bunch of sines and tangents in it. So it's amazing that he figured it out without the electromagnetic theory. But then once, I forget, Maxwell and all these people developed the actual idea of the electric vector and the magnetic vector functioning in time, you can actually match them up for the part of the beam that's on top of a surface and reflecting, and part is going down, refracting inside, and you can, say they add up right to conserve energy and have the phases match and everything, and you come out with the same formula with sines and tangents that I'm not going to write until we study refraction, which I put off to the end of the quarter because it's not central to the topics that we really want to study in this course. But so the Fresnel reflection coefficient. So the formula is in the book, and you'll see it's pretty complicated. But for your homework, for the bounces, did you all get my email that when I looked at the code base, the only thing that you really need to add is the specular component of the reflection, because the diffuse component and the shadow field arrays are already in that code, that reference stuff that I put in there. You just have to change the material type to make it allow, some, why don't you just make this constant, times the light coming in from another direction. Basically, if here's the viewing ray, and at the end of the period I'll talk about viewing rays and how to compute the surface normal, at least for a sphere or a plane. You can compute this reflected direction. Then you have to start a ray here going off in this direction, see what it hits, and figure out what color that would be multiplied by the specular coefficient and contribute it to this ray. So that's where the recursive calls come in, and that part isn't in the code. So what I want to tell you at the end of the period is how you compute this n and how you compute the initial viewing rays, which is in the code, but I want to describe it if I have time for it. But let me now talk about the Phong model. And this is for glossy reflection. And the idea there is it won't reflect only in the mirror direction, but if you sort of plot the distribution function as, say, heights above this unit sphere, it'll be very peaked near the perfect mirror direction. So it can be sort of an approximation. Depending the shinier it is, the narrower and steeper the peak will be. So he wanted to invent a function that had a sort of peak in this specific reflected direction. And so what he said is, let's take the reflected direction is this kd times the ln d omega n n dot psi. That's the diffuse reflection. And he wanted to add on another term, ks, times the same, I've been calling it intensity in, radiance over solid angle. But now he said, let's look at r dot theta, which is the outgoing, this is the outgoing direction that you're actually viewing it in, or, measuring how much reflected in. And there's a certain angle, say here, alpha, between this theta direction that you're viewing it in and the perfect mirror direction. And if you take, this is the cosine of that angle, and you take it to some high power. Right? So if we take cosine theta to the first power, we'll get a function that looks like that. But if we take cosine squared theta, then we'll get a function that looks like a piece of a raised sine curve like that, right? It goes, you know, there's a formula for cosine squared theta, and I think it's 1 minus, or 2 cosine theta minus 1, right? Cosine 2 theta minus 1. Here, cosine 2 theta would be spread out like that. And if you have that, and I guess you have to, if it's 2 theta, you're going to then move it up like this, and then take half. What do I have to do? I have to make it half as high, and then add 1 to it, and it'll move up like that. If you take a higher power, it'll become more peaked. And if you take like the 10th power, it'll get really peaked, and so on, because you're just taking these numbers which are less than 1 and raising them to higher and higher powers to make them get smaller and smaller. But the numbers really close to 1 still are part of this peak. Because even though if they're close enough, even if you take them to a high power, you still have something substantial left. And so by adjusting this n, you can adjust the size of the peak. It's sort of not conserving energy, right? Because this represents radiance out, and so less and less radiance is coming out. So once we actually are trying to sample the Phong distribution, we have to be more careful to make it, you know, to make, instead of Ks be a formula, something that just is, you stick it in and make it look pretty. If it's really going to represent a physical fraction reflected, then we have to actually, just like we got the pi, we'll have to integrate this thing over the hemisphere and see how we have to normalize it. Okay, so this is the formula. Now, what does that say about the specular BRDF? So what FR do we need to get this term? We need what multiplies this light coming in. And what multiplies the light coming in has times cosine theta has got to be Ks times this R dot the light over C dot N, right? Because the n dot c is what you have to multiply this light by to account for the foreshortening. And that foreshortening cosine of theta wasn't in this formula. Which means if you want this formula to come out using a BRDF that says multiply it by the cosine theta to account for this potential slant irradiance spreading it out, this cosine theta has got to be in the denominator. Okay, well, if that's the case, then this doesn't satisfy reciprocity or anything. And let me give another modification of it, which is a Blind's modification. And actually, Blind fixes his there is a way to fix Blind's, so to make it satisfy reciprocity. What Blind did was, here, let me draw a picture again. Let's say here is the normal, and I'll draw a much more slanty psi. And so it's a much more slanty R coming out. And suppose I have a theta here. So here's my difference, this alpha that I called, that I'm taking the cosine of that to a power for Phong's. What Blind proposed is to compute a vector which is halfway in between these. Which he calls H. So we can just define H as the sum of these unit vectors, theta plus psi, right? But that sort of parallelogram thing, that'll get something pointing halfway in between. And then if we want to make it a unit vector, we'll just divide by its length. And then what Blin proposed to use is to take a formula that would use K for the specular term. You know, I won't add on the diffuse term. Maybe it's purely specular and doesn't have any diffuse part. Although what you probably want to do for homework is let every material have a diffuse coefficient and a specular coefficient. In fact, the way it's set up, they even have ambient coefficients, which is sort of a hack to account for the light coming in from all directions if you weren't going to do global illumination. So Ks times n dot h to some power. So if you do that, then still it doesn't have the cosine factor in it, so that if this is the shading term, the corresponding FR is going to be Ks n dot h to the nth power over n dot psi, right? Because just like Blin, just like Fang, he didn't put the cosine theta in his shading term. And that means in terms of the BRDF, it has to be in the denominator. And now this also doesn't satisfy reciprocity. This term does, because since this is the angle halfway in between, the dot product with n dot h dot psi is the same as the dot product with h dot theta. These two angles are the same. Maybe I should put arrows so you can see where they end. This one is the same as that angle. So there is a modified Blin-Fang model which adds the specular term is, well, here, why don't I write them both this time? It's Kd, the diffuse reflectivity, plus the specular reflectivity times n dot h over n dot psi. If you put that in the shading formula, then when you think multiplying, if this is in the bidirectional reflection function, then it'll, let's see, what did I say? I want to say this differently. I'm sorry, this is the shading formula. So it's Ks, this is the shading term. Let me just do it that way. If you put this in the denominator of the shading term, then the bidirectional reflectivity function is Ks n dot h. Let me think about that to the n. Do I want to put it in the numerator or the denominator? Didn't bring my book with me, so I'm a little confused. Yeah, I think this has to be in the numerator. If I put n dot psi in the shading formula, it's as if I multiplied this BRDF already by the cosine formula, like I was probably doing on what I just erased there. Right? Stick this term in for the DL coming out. It's got the cosine in it, times the BRDF. If that is going to give the shading term, like this, then the BRDF factor is without that thing in the denominator. Here it was, in order to give this shading term, But if I take it out of the denominator, I just have a different way of applying the shading, and now I do have reciprocity because this angle is the same as that angle. So that's the modified one. And it turns out that if all these vectors that I've drawn are in the same plane, alpha is twice beta, right? Because the angle between psi and n is, what am I going to call this? I don't know, gamma. Is gamma plus beta. And that angle here is also gamma plus beta because R is the perfect direction, perfect mirror reflection of this incoming light. And let's see, what does that mean? This much is gamma plus beta, and this is gamma, so this much must be gamma minus beta, right? And that means their difference is 2 beta. So alpha is 2 beta. So if you want to get the same highlight for a Blin-Fang exponent m, you're actually going to have to make the original Fang exponent be higher to make the highlight get smaller, right? Because you want it to correspond to an angle half as big. And if you apply basically the the Taylor expansion of cosine, looks like 1 minus cosine of x looks like 1 minus x squared over 2 plus other terms. You can figure out the shape, at least for the top of this peak. When it's curling down, it's basically the top little piece of the parabola. To make that parabola twice as thin, you have to actually make the exponent 4 times as big. So that means for a given shininess factor m in the Fang, to make this, in the Blin-Fang, to make the Fang one look like it has the same size highlight, you actually need the n to be 4 times as big. Okay, so then the book talks about the Torrent Sparrow Cook shading, which actually is physically in terms of microfacets. In other words, you think of the surface as being made of a bunch of little wiggly facets, and which are mirror-like facets, and maybe one of them is actually sloped perpendicular to this h direction. It's that microfacet that actually gets you in this off-specular direction. And then it's the distribution of the microfacets. How many of them have tilts a certain amount away from the normal, which will give you the shape of that glossy highlight. And we'll talk about that near the end of the quarter. So, because what I want to talk about the rest of today is the 2 things I said I would, how you compute normals and how you compute I rays. So for the normal, if you have a polygon, say a triangle, here's V0, V1, V2, you can get a vector perpendicular to that triangle by taking the cross product of these 2 vectors, V0 minus V1 cross V2 minus V. I'm sorry, I want to think the vectors is going this way and that way, so it's going to be V1 minus V0 times V2 cross V2 minus V0, and that'll point to you, away from the blackboard in this case, perpendicular to the plane of the triangle. So if you orient all your triangles so that they look counterclockwise when from viewed out from outside, then the right-hand rule is always going to give you an outward-facing normal, which is sort of the outside surface of this object that's bounded by all these triangles. For a sphere, it is a special case of general implicit surface. So if we have any kind of surface given by f of x, y, z equals 0, then if we look at a nearby function, and we look at the gradient as this function varies, the gradient of f is normal to the contours of constant value. Right? That's just some property that comes out of calculus. So we can take the normal is the gradient of the function, and the unit normal is, if you want to normalize it, divided by its length. So for a sphere, now we have this perfectly round sphere with a center C, and we have some point, say, P, on the surface of the sphere, which is coordinates x, y, z. I guess the equation of the sphere is f of x, y, z. What I said before, it was p minus c squared minus r squared, where r is the radius. And I can write this as, say, x minus, maybe I write it on the next board so I have room to write the gradient. Oops, that shattered. F of x, y, z equals x minus xc squared plus y minus yc squared plus z minus zc. These are the xc, yc, zc are the coordinates of the center of the sphere, minus r squared. That's the thing we set to 0. So that's f, and the gradient of f then has components. The derivative with respect to x is twice x minus xc times the derivative of what's inside, which is just 1. And this y component is twice y minus yc, and the z component is twice z minus zc. So that's really just twice this vector p minus c. And that means now if we take n equals the gradient of f divided by the absolute value of the gradient of f, that's 2p minus c divided by the absolute value of 2p minus c. Really, that's the same as the canceling the 2's, p minus c normalized. So if I go back to this board, basically it says you look at this vector from the center of the sphere to the point, and you take the normal vector to go in the same direction, just making it a unit vector. And because this radius vector is perpendicular to the tangent plane at that point, that is the surface normal. So that's the normal that you can use when you're computing your reflecting rays for homework to do off of spheres. And if you have a triangle for an object made out of polygons, then the normal I showed you on the other board will work. So finally, we want the viewing rays. And so for that, we need to think about how you define a camera. And if you look at that input file in the scenes directory, it defined it in terms of an eye point and a look at point. So the look at point is the point that you're aiming the camera at. Okay, and then somewhere perpendicular, say at a unit distance from the eye, we have the view plane. Say this is 1, so it's we can form a look direction. Maybe I'll start it a little higher on the board. Equals look at minus I over the absolute value of this vector. Right? So it's a unit vector in the direction we're looking at. But instead of asking the user to specify a unit vector, it's easy for him to just specify a 3D point in the model that he wants the camera to aim at. Okay, and then the other thing, if you remember viewing from a basic graphics course, your camera might not be aimed exactly horizontally, but maybe if it was aimed at that corner, you would want the vector representing that vertical direction to look like it's vertical. That means that a vector whose tail is at the point you're looking at and is pointing in this up direction, when it's projected on the screen, should project to a vector which is vertical with respect to the screen, which means that it's really, that direction is the intersection of the plane or the triangle, like this. The plane through your eye and the look at point, that's through this axis. It's rotated around so that plane contains this up vector. And then when you project that up vector, it ought to come to be the y-axis of your viewing coordinate system, which means the x-axis of your viewing coordinate system has got to be perpendicular both to this plane and this line. I guess if it's perpendicular to that plane, that means basically it's perpendicular to both this vector in that plane and that vector in that plane. So that means we can get the, I'll call it u, because it's not the x-axis, it's the sort of the u-axis in this plane. And that's going to be look, direction, cross the up vector. Right? This times is a vector cross product. So that, I guess by the right-hand rule, that's making x go to the right in this plane. And so the up is going to go up instead of down if you do it in that order. And then the v is going to be, well, let's just normalize it. And then we have the look at direction is now a normalized vector like that. And we've just normalized u. So that means the right-hand rule can give v as the cross product of u times the look direction. Not times, cross look direction. Okay, so there's one other thing that the user specifies, and that is basically this angle. Because, you know, if you change the not the f-stop, the zoom of a lens, focal length of a lens, you can look a wide angle or small angle. And so what you want to do is specify this angle. And given that angle, what you want to compute is the tangent of, well, so usually you specify the whole opening angle, and then you want, say, opening. Tangent of opening over 2 is basically from the center of the sphere to of the screen to the right side of the screen. And so what the code does is they multiply u, the vector, by this length. T-H-F-10 HFOV, which is the half view angle. And what they do then is, if this vector is 1, this vector goes all the way to the side of the screen. And then minus it goes to the other side. And similarly for V, but instead of specifying this direction, they say you can also specify an aspect ratio, which is the ratio of the number of vertical pixels to horizontal pixels in terms of resolution. And then you can compute it that way instead of specifying another angle, because you also want to specify the resolution. Like I think the default case in the input file is square, in which case this really would be the same multiple that you have to multiply it by. Oh, so this is a scalar multiple, and I'm multiplying it by the vector u. Right, so this was a unit vector, and by the time I'm done, it's actually a vector going to the side of the screen to make that correct angle of opening. And then once you've got all those vectors, then you can just find how to spread out a normalized device coordinate screen, which is a square going from -1 to 1 in x and y. So this is -1, -1. This is 1, -1, and so on. So both x and y go from -1 to 1, and then your viewing direction, if you know an xy in this coordinate system, it's going to be this vector plus the vector in this plane gives you the fraction of the way to the edges of the screen. So if x goes from -1 to 1 and y goes from -1 to 1, then to get, in terms of the width of the screen, to give you that correct opening, it's going to be the viewing direction plus this scalar x times this u direction plus the scalar y times this v direction. It's not only direction, it's actually multiplied by a number to give you the right angle of opening. Okay, so how do you find x and y if you have a pixel? Basically, you know that this x-axis is divided into equal pieces, and there are x-res of them. And so similarly for the y. And if you have square pixels, what you want to do is you want to find the ray through the pixel center. So the ray through the first pixel center is x min, and that's equal to -1 plus half the width of the pixel. So dx, the width of the pixel is, I guess, the total width over the x resolution. And x min is -1 plus 1/2 of dx, right? Because you're only going halfway across the pixel. And that means the x for column I in your raster array is x min plus I times dx, right? dx should have been dx. You know, how many spaces over from the one with index 0. And similarly, yj for pixel ij is going to be similarly y min plus j times dy. For square pixels, I guess, well, for the same resolution, x and y, it'll amount to the same thing. So this x and y then is what you put in this equation to get your viewing ray. So that's how you get the initial viewing ray for each pixel to do the homework, and that code is already in that package I gave you. I just wanted to explain what it was doing. So now I'm a minute late. Sorry. I'm making up for ending early last time. So I'm done.